Hello, and welcome to our third to last section of the year and also chapter 5. So, this chapter is about differential equations and slope fields. We've kind of dealt with differential equations before. For us, it was more kind of like implicit equations that we were dealing with, but now it's going to look a little bit different because we're going to have a mix of derivatives and regular functions at the same time in the same equation. So that's what differential equations means. So here is an example of a differential equation. Y prime plus 2y equals 0. So here you see you have a derivative, you have regular y, and they're both in the same equation at the same time. So in this first section, we're not quite solving for y yet. We're going to be given a solution, and then we just need to verify that it's true. So we're trying to verify that y equals e to the negative 2x is the solution. In order to do that, we're basically taking this equation, because that's what they're saying y equals, so that's our function. We want to make sure that if I took 2 times this function and then added it to the derivative of this function, all of that added together should equal 0. That's what we're trying to check for. And it's supposed to be true because it says verify. So they're telling us this is going to be true. You just have to show your work for it. So whenever it says verify, I'm not trying to make sure that this is actually an answer. We already know that. But you have to show the work to prove that it is an answer. So that's what we're trying to do. So first, let's actually find y prime. So the derivative of y. That way we can plug it in here. So finding the derivative of e to the negative 2x requires chain rule because we've got like a more complicated exponent here. So it'll just be for e, it's just itself as the derivative, but then multiply by negative 2 because that's the derivative of the inside. So y prime is just negative 2 e to the negative 2x. Okay. So now we're going to plug in y prime into our original equation and the y that they gave us into the original equation. So that gives us that negative 2 e to the negative 2x stands for y prime plus 2 times y, which was e to the negative 2x. And that should equal 0. So this is what we're checking for. So I'll just put a little question mark there with the equal sign because I don't know quite for sure if it's supposed to be true or not. And then adding this together, we have negative 2 e to the negative 2x plus 2 e to the negative 2x. Yes, that does equal 0. Check. Yay. So now we've shown that this actually works. Okay, for my next example, I want to determine if each function is a solution of y double prime plus y equals 0. So I have 3 different options here. I want to check if any of these work for this differential equation. So this y double prime plus y equals 0. Since I have y and y double prime in it, so that means I need to find the second derivative before I can plug it in. So I'm just going to go ahead and start with option A. The first derivative is just going to be the derivative of sine, which is cosine. The second derivative of cosine, is negative sine. Okay, so now that I have the second derivative, let me plug it back in into my original differential equation. So that'll give me negative sine of x plus y, so plus sine of x. Does it equal 0? Yes. Yes, it does. So that means y equals sine x is a solution. Okay, let's try option B. So y equals c e to the x, where c is any real number. So they're just saying c is some constant. They're not specifying what constant it is, so it could be anything. So let me find the first derivative first. So since I have a constant being multiplied, it'll stay there, and then e to the x would be the derivative. That doesn't change. Y double prime should be exactly the same then. I have a constant in front, e to the x. Okay, so if I plug my second derivative and the original back into my differential equation, that'll give me c e to the x plus c e to the x. That does not equal 0, so that means y equals c e to the x is not an answer. Okay, last one. Let's see if this one works. So the first derivative of negative cosine of x is going to be negative sine of x. Oh, sorry, positive sine of x because the sign will change. And then the second derivative would be positive cosine of x. Okay, then taking my second derivative of cosine of x, adding it to my original, which was negative cosine of x, this does equal 0. All right, so that means both y equals sine x and y equals negative cosine x are solutions. Okay, which means you are able to have multiple solutions to differential equations. Okay, so now that we know that you can get multiple solutions for our differential equations, the next thing that I want to be able to do is to find a particular solution. So we're basically trying to say, like, out of all the different solutions that we have, we want just one of them. And in order to find that one, you're going to need to be given an initial condition. So for my example, I want to first verify that y equals cx to the third power is a solution to x times y prime minus 3y equals 0. Then find the particular solution if y equals 2 when x equals negative 3. So right here, when they tell you this information about like a specific point, those are your initial conditions. Without those initial conditions, we can't actually find a particular solution. We're just going to be given some function. Okay, so let's do this. If we're trying to verify that cx cubed is a solution to x times y prime minus 3y equals 0, we do need to figure out what y prime is going to be in order to be able to plug in fully. So, starting with that, I have c times x cubed. C is just a constant, but the derivative of x cubed is 3x squared. So this is going to end up being c times 3x squared. So then plugging in, I'm going to have x times y prime, which is c times 3x squared, minus 3 times y, where y is cx cubed. Does this equal 0? So multiplying this out and kind of combining like terms, I end up with c times 3x cubed minus 3cx cubed. Well, yeah, those are the same, so when we subtract them, they equal 0. Cool. So this is a one of the solutions then of our differential equation. So now to find the particular solution, we know that this is one of our solutions, y equals cx cubed. So plugging in y equals 2 and x equals negative 3, then we can solve for c. So that ends up giving me c equals negative 2 over 27, because negative 3 cubed is negative 27, and then I'm going to divide it over to the other side to get c by itself. So that means my particular solution is going to be y equals negative 2 over 27. I'm just plugging in c into my original solution, x cubed. Okay, that'll find me the particular solution. Here's another similar example. So if you want, pause here, try it yourself, and then let's come back together and check our work. Okay, so hopefully you paused and did it and got the right answer. So you should have ended up with a particular solution of y equals 2 times e to the negative x squared power. So first we had to verify by finding y prime. You should have gotten negative 2x times c times e to the negative x squared power. Then since it did work, then we're going to plug in y equals 2 and x equals 0. That left us with 2 equals c times e to the 0th power. Anything to the 0th power is just 1, so that gave us c equals 2. And then we could plug that in for c into our original solution that they told us. Okay, hopefully nothing was too crazy so far, so we move on to the last part of this section, which is called slope fields. So slope fields is basically a graph that shows all the different solutions that a differential equation could have. So let's do an example. We want to be able to sketch a slope field for the differential equation y prime equals x minus y. Okay, so here's my graph that I want to use. So you see how there's a bunch of dots. We're basically trying to draw out the slope at each of those dots. And if you look at our equation, we have it set at y prime equals x minus y. Y prime is just the first derivative, which is also, remember, derivatives are just slopes. So we're basically saying at each of these dots, whatever the coordinates are, plug those in for x and y. And then that'll give you the slope at that point. So let's say, I'm just gonna make kind of like an XY chart here, but slightly more complicated. I'm gonna do an XY Y prime chart. So let's say we're trying to look at this dot right here. This dot has coordinates of 1, 1. So x is 1, y is 1. What's y prime? So y prime is just x minus y, so x minus y would be 0. A slope of 0 is just a horizontal line, which means at this dot with the coordinates 1, 1, we're going to do a small horizontal line to represent a slope of 0. And then we're just going to keep going. So now let's say we're trying to figure out the slope right here at this dot, which is the coordinates 2, 1. So 2 for x, 1 for y. 2 minus 1, plugging that into our equation gives us a slope of 1. A slope of 1 is like slanted positively, like this. So that'll be our slope at that point. And we continue doing this for all of the points. You don't have to write it out every time. It just helps because it's visual. But this is an easy equation, x minus y. So this point right here is 3, 1. So 3 minus 1 would be 2. So 2 is a positive slope, so it should be going upwards. And it's a little bit more steep because a slope of 2 is steeper than a slope of 1. So it doesn't have to be like super accurate, but we're basically trying to do this for the entire graph so that we can kind of see what the shape of the solutions or the general solutions are going to look like. So if we keep going right here, this point is going to be 1, 2. So subtracting those would be negative 1. Slope of negative 1 goes this way. Here would be 2 minus 2, which is 0. This point would be 3 minus 2, which is 1. 3 minus 3, 2 minus 3, 1 minus 3. 1, 0 would be 1, 2, 3, 1, negative 1 is 2. Okay, so I continued on with the entire graph, all the dots on it. And so you can kind of see what this looks like now. You can see how the slopes, so if we're talking about a slope field, that means each of these little points has the slope of what it should be about at that point. So if you look, the slopes kind of point you in like this kind of curved shape, and it might like change depending on where you are. But you know how we were talking about there's particular solutions versus like the general solution. So this kind of shows you all the different possibilities. So if we know one of the initial conditions, like let's say they told us y equals 2 and x equals 0, then that means x equals 0, y equals 2 would be this point right here. So we know that slope would be part of our particular solution. And if we kind of follow it along, then we can kind of see where it goes. But that's the point of a slope field, is to be able to visualize all the different solutions. And that's it for this section. It's nothing crazy. I'll post the assignment, and then hopefully we finish off the year with just 2 more sections after this. Cool. Bye.